Welcome to the Deep Dive. We sift through the latest research, the latest insights, to get you well-informed, fast.
Glad to be here.
Today, we're doing something pretty special, I think. We're looking deep into space.
But not just looking at space now.
No, exactly. We're looking back, way back, billions of years. It's like a cosmic time machine.
It really is. And the breakthroughs recently, they're letting us dial that machine back further than ever.
So that's our mission today, this deep dive. We want to unpack how scientists are doing this, how they're tearing into the very beginning, the cosmic dawn.
That's the term, yeah. We'll explore the tech, the fundamental limits, why looking far away is looking back in time.
And we'll hit the big stuff. Yeah. The ultimate horizon, James Webb Space Telescope versus, its predecessors like Hubble.
And even some really exciting ground-based stuff, too. Plus, the discoveries, the earliest galaxies, this weird jellyfish galaxy.
Okay, let's dive in. The core idea first. This cosmic time machine thing, it all comes down to light speed.
Pretty much. Light travels incredibly fast. What is it, about 300 million meters per second in a vacuum?
About 985 million feet per second, yeah. But crucially, it's not instant.
Exactly, it's finite. So that light hitting our telescopes from, say, a distant galaxy, it left a long, long time ago.
So if we see a galaxy a billion light years away...
We're seeing it as it was a billion years ago. It's a snapshot from the past.
Simple concept, but whoa. Okay, but here's where I, and probably others, get tripped up. The universe is, what, 13.8 billion years old?
Roughly, yes. That's the current estimate.
So you'd think the edge of what we can see is 13.8 billion light years away.
That makes intuitive sense, but it's actually wrong.
Right, because the universe is expanding.
Precisely. That's the key takeaway. While that light was traveling towards us for 13.8 billion years, the space itself between us and that source was stretching, expanding.
So the thing that emitted the light is now much further away.
Much, much further. The edge of the observable universe, the stuff whose light has had time to reach us, is now estimated to be about 46.5 billion light years away.
Making the diameter double that, 93 billion light years.
You got it. It's staggering. 13.8 billion years old, but 93 billion light years across, all thanks to expansion.
Mind-bending stuff. Okay, so if that's the edge of the observable universe, what's the absolute furthest back we can possibly see, like the ultimate horizon?
That would be the cosmic microwave background, the CMB.
The afterglow of the Big Bang.
Exactly. You can call it relic radiation, the afterglow.
Yeah.
It's basically microwave light filling all of space. And it's probably the strongest evidence we have for the Big Bang model. It really underpins our standard cosmological model.
So when did this CMB form, and why is that the limit? Why can't we see further back?
It formed around 380,000 years after the Big Bang. Before that time, people sometimes call it the cosmic dark ages. The universe was just this incredibly hot, dense soup.
A mash of particles, protons, electrons.
Yeah, all mashed together. And crucially, it was opaque to light. Think of trying to see through a really thick, incredibly hot fog. You just can't.
Okay.
But as the universe expanded, it cooled down. Eventually, it cooled enough for protons and electrons to combine and form neutral atoms. And that event, sometimes called recombination or decoupling, basically cleared the fog.
So the universe became transparent.
For the first time, yeah.
Yeah.
The light that was bouncing around in that fog was finally free to travel across space. That light, stretched out over billions of years into microwaves, it's the CMB. It's the surface of last scattering, the earliest possible picture.
Wow. So the stuff that actually emitted that light back then, where is it now?
Because of that expansion we talked about, the matter that emitted the CMB light we see today is now calculated to be right out there at the edge, about 46 billion light years away.
Incredible. And its discovery back in the 60s.
Yeah.
That was Penzias and Wilson, Nobel Prize stuff.
Huge moment for cosmology. Absolutely. Changed everything.
Okay, so we need amazing tools to see these faint, ancient signals. Let's talk telescopes. Hubble's the icon, right?
Definitely. The Hubble Space Telescope, launched in 1990, still going strong. It orbits relatively close, about 340 miles up.
And it sees mostly visible light and some UV and infrared.
That's right. Near ultraviolet, visible near infrared. Its sensitivity is amazing, can see things 10 billion times fainter than our eyes.
And the resolution, like seeing a dime from 86 miles away.
Something like that, yeah. About 10 times sharper than typical ground telescopes. It uses gyroscopes, very precise pointing systems.
And those servicing missions, that was unique to Hubble, wasn't it? Astronauts actually going up there.
Totally unique for a major space telescope. 5 missions, Huge benefit. They fixed the initial mirror flaw, upgraded instruments, extended its life way beyond what was planned.
But challenging, I bet. Risky.
Extremely complex and risky, yeah. But it kept Hubble cutting edge for decades. Still, it had its limits, especially for seeing the very earliest stuff.
Why was that?
Well, a couple of things. Being relatively close to Earth meant it was still affected by Earth's heat, its infrared glow, which kind of dazzles sensitive infrared detectors.
Oh, okay.
And the light from the truly distant earliest galaxies is stretched so much by expansion redshifted that it moves out of Hubble's best range, mostly into the deeper infrared. It could see back to about 400 million years after the Big Bang, but not much further.
Enter the James Webb Space Telescope, JWST, designed specifically for that infrared light.
Exactly. That was the whole point, to capture that incredibly redshifted light from the cosmic dawn.
So redshift is reason number one for infrared. What else?
Dust. Lots of interesting stuff, like forming stars and planets, happens inside thick clouds of dust and gas. Visible light gets blocked.
But infrared can get through.
Longer infrared wavelengths can penetrate that dust much better. So Webb can see inside those stellar nurseries, see things Hubble couldn't.
Like brown dwarfs, protostars, that kind of thing.
Yep. And also just cool objects, things that aren't blazing hot, like young planets, or even just, people they emit heat, which is infrared radiation.
Right. Okay, so Webb needed to be optimized for infrared, and that meant going somewhere very different from Hubble.
Very different. Not orbiting Earth. It orbits the sun way out at the second Lagrange point, L2. That's about 1.5 million kilometers, nearly 1 million miles away from Earth.
4 times further than the moon. Why L2?
Stability and cold. At L2, Webb can keep the sun, Earth, and moon all behind it using its giant sun shield. This lets the telescope get incredibly cold below 50 Kelvin, minus 223 Celsius.
Which is crucial for infrared detectors, right? They need to be cold so their own heat doesn't interfere.
Absolutely critical. That sun shield is a marvel of engineering. 5 layers, thinner than a human hair, the size of a tennis court. One side faces the sun and gets hot. The other side stays freezing cold. It had to deploy perfectly.
And the mirror, much bigger than Hubble's.
Oh, yeah. 6.5 meters across, made of 18 hexagonal segments of beryllium, coated in gold. Gold is excellent at reflecting infrared light.
Gives it about 6 times the light collecting area of Hubble.
Something like that. Meaning it can see things about 100 times fainter.
Wow. And lining up those 18 segments must be intricate.
Incredibly precise. Tiny motors adjust each segment with nanometer accuracy. It's like a high-tech dance to make them act as one perfect mirror.
But unlike Hubble, no astronaut servicing for Webb, right? Too far away.
Correct. Designed for a long life, but not for hands-on repairs. There are some provisions for potential robotic servicing in the distant future, but nothing like the Hubble missions.
And it wasn't exactly a smooth ride getting it launched. Cost overruns, delays, the telescope that ate astronomy.
Yeah, it got that nickname. It was hugely ambitious, complex, pushed the boundaries, and it's had challenges since launch too, like micrometeoroid impacts. But they're managing those.
It's delivering, though. But it's not just space telescopes. You mentioned a ground-based breakthrough. CLASS.
Yes, the CLASS Observatory, high up in the Atacama Desert in Chile. Very dry, very high altitude, over 16,800 feet.
And they've managed to detect signals from the cosmic dawn, from the ground. I thought the atmosphere was too much of a problem for that.
That's what makes it so significant. As the project leader said, people thought this couldn't be done from the ground, but they developed techniques to filter out atmospheric interference and isolate those faint microwave signals from the universe's first billion years.
That's amazing. What's its main goal?
It's surveying about 75% of the sky at specific microwave frequencies, mapping the polarization of the CMB, looking for signs of inflation, and studying that cosmic dawn era. It shows ground-based innovation is still crucial.
So with tools like Webb and CLASS, what are we actually seeing from that early time? Tell us about these record-breaking galaxies.
Okay, get this. JWST found 2 galaxies, JWST 14.0 and JWST 14.1. The first one, Z14.0, is seen at a redshift of 14.3.
Which
means we're seeing it as it was just 290 million years after the Big Bang. That's incredibly early. Like the universe was only 2% of its current age.
Wow, barely out of the gate. And the other one?
Z14.1 is seen slightly later, around 300 million years after the Big Bang. Still firmly in that cosmic dawn period.
What's so surprising about them, especially Z14.0?
It's stupendously bright, according to the researchers. Almost 5 times brighter than the previous record holder, which was seen at 325 million years.
Why is that a puzzle?
Because Our models of how galaxies form, based on how dark matter halos are thought to clump together and grow, didn't really predict something that massive and bright so early. It suggests maybe galaxy formation got started faster or was more efficient than we thought. It's a cosmic conundrum, they're calling it.
How do they confirm the distance is real?
They look at the spectrum, the breakdown of light. They found a clear Lyman break, a sharp drop-off in light at a specific wavelength, which is like a definitive fingerprint for these extremely distant objects.
The analogy they used, finding a smartphone in ancient Roman ruins.
Yeah, it implies this galaxy is maybe surprisingly evolved for its time, and hence there could be many more, perhaps less bright ones, out there waiting to be found from that era.
And this was found in a tiny patch of sky, like a grain of sand held out.
Exactly. Shows how much more JWST might uncover just by looking longer and wider.
Okay, beyond the most distant, what about this jellyfish galaxy? That sounds cool.
It does. This is another potential JWST discovery reported recently. It looks like a jellyfish galaxy, seen about 12 billion light years away. So we're seeing it as it was when the universe was quite young, though not quite cosmic dawn territory.
What makes a galaxy a jellyfish?
They typically live in dense galaxy clusters. As they move through the hot gas in the cluster, that gas pushes against the galaxy's own gas. It's called ram pressure stripping. It strips gas out of the main body of the galaxy, forming these long, trailing tentacles of gas and newborn stars.
So it looks like a jellyfish trailing its tentacles.
Precisely. Finding one potentially this early, 12 billion years ago, is interesting because it tells us about the environment of galaxies back then and how these stripping processes, which can both trigger star formation in the tails and shut it down in the core, were already shaping galaxies. Needs more confirmation, but it's exciting.
Webb's doing so much more too, right? Exoplanets, finding molecules.
Oh, absolutely. It's revolutionizing exoplanet studies, looking at atmospheres, even hunting for tricky things like exomoons. It's given us stunning views of Jupiter, detected complex organic molecules 12 billion light years away. It's really a game changer across the board.
Okay. This ability to look back billions of years is amazing. Let's do that thought experiment. Could we use this principle to see Earth's history? Like if I teleported 200 light years away instantly and aimed a super telescope back at Earth, would I see the 1800s?
Theoretically, yes. The light from Earth in the 1820s would just be arriving at your location 200 light years away. So in principle, you'd see that past.
But there's always a catch.
There's a huge catch. Several, actually. To resolve any meaningful detail, say sea cities, forget about people you'd need a telescope with a mirror.
Yeah.
Well, calculations suggest something over 9,000 kilometers across.
9,000 kilometers. That's like wider than Australia.
Exactly. Yeah. Utterly impossible. An object that massive would collapse under its own gravity into a black hole long before you finish building it.
Okay, so physics says no. Any other catches?
Even if you could build it, you'd need incredibly long exposure times to gather enough photons, enough light particles to form a clear image. You wouldn't be watching history unfold in real time. Plus, Earth's moving, its atmosphere blurs things. Yeah. Fun idea, but strictly science fiction for now.
Right, a bit of a bummer. No checking on the dinosaurs then. Okay, shifting from looking back to looking out, what about our own reach? Voyager 1. Still going.
Still going. Launched in 1977. It's the most distant human-made object. As of mid-2025, it's about 166 astronomical units away. That's 166 times the Earth-Sun distance. Billions of miles.
And it's actually left this solar system.
It crossed the heliopause, the boundary where the sun's influence kind of peters out back in 2012. So yes, it's officially in interstellar space.
Wow. How far out is that in light travel time?
Light takes something like 23 hours to get from Voyager 1 to Earth now. It's projected to be 1 light day away sometime in late 2026.
And its journey continues way beyond that.
Oh, yeah. It won't reach the Oort cloud that hypothesized sphere of comets way out for maybe 300 years. It'll take 30,000 years to pass through it.
And eventually passing other stars.
In about 40,000 years, it'll come relatively close, 1.6 light years, to a star called Gliese 445. But it's basically drifting through the void.
Golden record.
Carrying the golden record. That time capsule of sounds and images from Earth, just in case someone or something finds it millennia from now. A message in a bottle flung into the cosmic ocean.
Incredible. Okay, let's bring this deep dive home. We've gone from the edge of the observable universe, the CMB,
through the incredible tech like Hubble, Webb, class that lets us peer back towards the cosmic dawn.
To the amazing discoveries of unexpectedly bright early galaxies, potential jellyfish, and even tracked our own farthest probe.
It really shows how we're mapping this vast, expanding universe, literally looking back through time piece by piece.
And every piece seems to refine or sometimes challenge our understanding of how it all began.
Absolutely. Each discovery doesn't just answer questions. It usually opens up bigger, deeper ones about cosmic evolution, galaxy formation, maybe even dark matter and dark energy. It's a constant process.
So the final thought for you, our listener, remember everything we've talked about, even the CMB at 46 billion light years, is just the observable universe, the bit whose light has had time to reach us. The universe itself might be vastly larger, possibly infinite.
What wonders, what knowledge might lie beyond that horizon? What will the next generation of telescopes, or maybe entirely new ways of observing, reveal?
Yeah, what stands out to you about how much more there still is to learn out there? Something to ponder.